Hello, in these slides I will explain certain things which I feel demand further clarifications and a few notes about whatever I have already taught. In particular, we will talk about reductions and valid computation histories, and that's a very powerful method, computation history method. So I start with a few things about reductions. So the first note that I would like to make is that a problem pi is undecidable does never mean that all instances of pi are undecidable. There may be some decidable or easy instances of pi which can be solved by deciders, but in general the problem pi is undecidable, which means that there is no general purpose algorithm that solves pi in all cases. Some cases may be easy. So for an example, I will look at the halting problem. So a decider may exist for some instances, but no decider in general for all problems. So I will take the case of halting problems. And we have proved this problem to be undecidable using a diagonalization argument. And there is no problem with that. We know that the halting problem is undecidable, although it is semi-decidable. Anyway, that's not an important issue. But most of the notes that I talk about in this context also apply to semi-decidable languages. Anyway, or non-semi-decidable languages. So, I will in particular show that one particular class of Turing machines can be decided when supplied as an instance for the halting problem. So in particular, these machines are of this form. They are those machines which do not have any transition of this form, delta p comma a equal to q comma b comma left. So all head movements are right. If the specification of M says that there are no transition marked as R as the third component, then this problem is decidable. We can build a decider which, after a finite number of time, finite amount of time, finite number of steps, can actually detect whether M is going to halt on W or it is going to loop on W. So a limited time simulation can actually decide this, but before giving you a complete proof of this decider, a complete construction of this decider, let me take a very specific example. I will come back to this example once more a little later, but for the moment let us look at it in this context. So I consider a Turing machine K with these specifications. It consists of three states: the start state, the accept state, and the reject state, and no other states. The input alphabet is 0, 1. Tape alphabet consists of 0, 1 and two other symbols that are very necessary. One is the left end marker and other one is the blank. And we have the following transitions. So since T and R are halting states, I do not need to specify transitions out of T or R, but I have to specify if the machine is in state S, it scans this or this or this or this, what it will do. So these are the four entries in the transition function that I must specify. For the left end marker, it's quite obvious. You have to move right. Okay. Don't override the right left end marker and continue to stay in the same state S. Then, if you see 0, immediately after, I would say, crossing this left end marker, if you see 0, accept and halt. If you see 1, reject and halt. If you see nothing, that is, there is the input is epsilon. So you see the blank, then also you reject and halt. So these specifications clearly indicate that this machine accepts all the strings over 0, 1 that start with 0. Okay. This is definitely, we know, a regular language, and this machine is a total Turing machine which accepts this language. In fact, it halts on all inputs in only 2 steps. Okay. So if you simulate this k on any input, a 2-step simulation will let you decide whether k is going to halt on that input w. The answer is always yes, because it's a total Turing machine. Now let us come to the more general case. So M is a Turing machine with no transition specified in its transition table with left head movement. Then let us give some input w for M. So M hash w is an instance of the halting problem for this particular machine. Now what you do, you just simulate M for only these many steps. Now note that M has no leftward transitions, no left movement of heads. So if M halts within these many steps, accept. Otherwise, reject. So I have to now claim or establish, justify that this reject decision is correct. So the point is that, once again, since M has no transitions with left head movement, one right transition is needed to go out to the input section, leaving the left end marker. Then, after these many steps, the number of symbols in the input, the head will eventually leave the input region, input portion. Okay, because it can never come back. After that, the head will continuously keep on scanning the blank symbol. And if this thing happens for these many steps, absolute value of q, the number of steps, then by the pigeonhole principle, some step must be repeated. Okay. And since we assume that M is a deterministic Turing machine, this immediately implies that the machine has started looping. And therefore, it has already started looping, and the same configuration will keep on, or same input to the delta function, transition function will keep on coming, and the machine will never halt. Okay. So, in general, if you have Turing machines of this form, the halting problem for this kind of Turing machines is decidable. But we know that this decider will not work if the Turing machine is allowed to move its head left. So this decider is not a general solution for the halting problem. It's a solution, it's a decider for a particular subclass of the halting problem instances. Okay. So that is fine. But then, if we make a reduction from one problem which is already known to be undecidable to a new problem, is it possible that all the instances do get mapped to only easy instances of pi? Is it possible? Okay, because we have seen that the halting problem itself has some easy instances. So likewise, pi may have some easy instances. So is it possible that all instances of the halting problem maps to these easy instances? The answer is no, it is not possible. Why? Because assume that, okay, why does the question arise? It arises because of the fact that this is a many-to-one mapping. So many instances of the halting problem may map to the same instance of pi, and these instances may be all decidable, easy. But that is not possible, because if it is the case, then the easy instances of pi do have a decider, and if all this reduction map produces only these easy instances, then this reduction followed by running this decider actually decides the halting problem. But we have seen that this halting problem cannot be decided in general. Okay, and there we have proved some other technique like diagonalization. Whatever it is, the halting problem is some problem which you already know to be undecidable. And therefore, a reduction cannot map. It is impossible that all instances of the halting problem will map to only easy instances of pi. So this gives you sufficient confidence in using this many-to-one maps for proving undecidability of new problems. Okay, so that's about a little bit I wanted to talk about decidability. Now, in the rest of the talk, I will concentrate upon some undecidable problems about context-free languages. In particular, I will look at this particular assumption. It is undecidable whether the complement of a context-free language L is again a context-free language. This was actually a question given in the tutorial exercises, and it was actually solved and put up in the website. So I will talk about this. And the solution that is put up in the web is not exactly fully correct. So what I will do, I will try to repair that solution. But that requires an understanding of quite a few concepts. And these concepts are rather, I would say, non-trivial. That's why, mostly because of that, I went into these presentations. Okay, so what is presented in that solution is that it's actually a reduction from the complement of the halting problem to the set of all context-free languages L specified by context-free grammars such that their complements are context-free. So the map was simple, simply compute a context-free grammar of the complement of val comp m, w. That is, this is the language L which we have proved to be context-free. And a grammar exists for this complement of val comp m, w. So, in the solution, it is claimed that this construction is a valid proof of this assertion. I will now show that this proof has to be taken with a bit of salt. It's not exactly fully correct. We have to make a construction before applying this, I would say, reduction. Why? So let us see. It's a reduction, once again, recall it's a reduction from the complement of the halting problem to a grammar for this language. Fine. So, if M does not halt on W, then there are no valid computation histories of M on W. In particular, this set without this complement. So, val comp m, w is empty. Therefore, L, which is its complement, is the entire of delta star, and the complement of L is the empty set, which is, we know, to be a finite set, regular set, a context-free set, everything. On the other hand, if M does halt on W, what happens? Now we know there are one or more valid computation histories. Actually, we will see that there are infinitely many valid computation histories. And therefore, this is not equal to empty. And L is also not equal to delta star. Okay. But the complement of L, which is this val comp m, w, now this should be a non-CFL in order that this reduction from the complement of HP to M has to this language, set of all context-free languages such that they are closed under complementation. In order to make that reduction to make sense, this should never be a non-context-free language. Okay, but unfortunately this is not the case. A non-empty val-comp m, w may be context-free. It may even be regular. Okay, so I will give you an example where val-comp m, w is actually regular and therefore context-free. Okay. So first of all, it is important to note that every finite language is regular and therefore context-free. So, whenever this is non-empty, we must have infinitely many computation histories, all valid. Okay. Without that, it can never be a non-regular language. Forget about just non-CFL. Okay. So it must be infinite to start with. So, but that, if there is one computation history, valid computation history, there are infinitely many valid computation histories. This fact is embedded in the definition of val-comp m, w. There are two reasons. First, there are two reasons for this to be infinite. First reason is that we are allowed to repeat the halting configuration at the end. The last configuration must be a halting configuration at state T or R, and we can repeat that configuration as many times as we want. Okay. And the second thing for which the val-comp m, w language can be infinite is that at the end of each configuration, we can append as many blank symbols, some portion of the tape, finite, but as many as we want. Each configuration can be appended by this symbol star. Okay. For these two reasons, val-comp m, w is infinite, and therefore the question whether it is going to be non-CFL is a legitimate one. Okay. But despite this infiniteness, non-finiteness, val-comp m, w can be a CFL. So this infiniteness alone does not guarantee non-CFLness of val-comp m, w. So let us see an example. So an example where val-comp m, w is not only context-free, it is just regular, although infinite. So once again we look at that machine K that I introduced near the beginning of these slides. So once again let me rewrite the specifications. This is a machine with the states S, T, R. Sigma equal to the input alphabet is 0, 1 and the tape alphabet contains two other symbols, the left hand marker and the blank, and the transitions are these four. So it essentially accepts all strings over 0, 1 that start with 0. We have seen that, right? Now I claim that for this machine val-comp m, w is regular. Okay, to be very specific, I take w to be the length 1 string 0. But this logic can be extended for any w whatsoever. Okay, but for simplicity, I am just talking about the input as a single length string 0. So the initial configuration, the first configuration and the second configuration can be written as regular expressions, the following regular expressions. The first one is this. The head is scanning the left hand marker and the input follows this. The state is S, and after that we can use as many blank portions of the tape as we want. Okay. This is the initial configuration. Okay. Or I would say this is a regular sub-expression that stands for the initial configuration. Each of these stands for the initial configuration. Now after this is read, the machine comes here state remains the same as S. Okay, so the next configuration is come here. Now it scans 0, and once again I may have any number of blanks included from the rest of the tape. Now once again it sees 0 in state S. It will move to the halting state T, which is the accept state. Keep the 0 as it is, move to the next cell and halt there. So the next configuration is like this. Let us come to the first non-blank or blank portion of the tape, and we can again append as many but only finitely many blank symbols from the tape as we want. And therefore a valid computation history of M on this K on this particular 0 can be generated by this expression, which uses this sub-expression C0, C1, C2. It is hash C0, hash C1, hash C2, hash, and then followed by as many times as you want to repeat C2, which is the halting configuration. So this is a proof that valcomp M, W can even be the language of a regular expression. So we have to do something in order to patch that proof. Okay. So to that effect, I first propose a generic construction that converts a Turing machine M and an input W to M to an instance, to a machine N and the same input W, such that this N has some properties. Okay. First, N is a non-deterministic Turing machine. M and N accept exactly the same language. The language of N is exactly the same as the language of M. Moreover, the halting behavior of M on W is exactly identical to the halting behavior of N on W. In other words, M has valid computation histories on W if and only if N has valid computation histories on W. So this is a fairly simple construction, but it is needed for a reason that we will see soon. First of all, let us assume that M has the accept state T and the reject state R. These are halting states. So N now marks these as non-halting. Mark the accept state T and the reject state R of M as non-halting. Instead, it adds two new states, to do new halting states, the new accept state T prime and the new reject state R prime. Okay. Now T and R are no longer halting. Okay. So I have to specify some transitions from T and R, if at all transitions. For that matter, I use a new symbol, but you can use the original blank symbol for this purpose. This was not actually very necessary. Anyway, let us have it. For no reason whatsoever anyway. Now, add these transitions. When the machine goes to T or R, and if it is scanning the left N marker, that is, it is on the first cell, 0th cell, leftmost cell, I will simply skip and continue to stay in the old accept state T. Just move right. Just move right. Then what I will do, note that this is a non-deterministic Turing machine, irrespective of whether N is deterministic or non-deterministic. Then the crucial things that I want to add is this. In state T, if the head scans anything other than this, it has two options. It may simply override that symbol by this new symbol, or for that matter by the blank symbol, move right. The second choice of delta, second choice for the machine to be in T, state T, is just jump to state T prime and halt. Likewise, if I look at delta R star for anything other than this left hand marker, It may continue to keep on moving right after replacing this by this symbol, or it may jump to the new reject state R prime and accept. So it is clear that if M accepts, then at some point of time M reaches the state T. Then what happens to N? N also goes to T, and there exist non-deterministic moves which allows it to jump to T prime and accept. If on the other hand M never goes to state T, N also never goes to state T, and therefore this kind of transition is never possible, this to this. Okay. So the language of M and N are exactly the same. On the other hand, if there are valid computation histories of M on W, that means some computation histories ending in T or R, then there are non-deterministic choices which lets this new machine N to end up in T prime or R prime. It may keep on moving, but at some point of time it may choose to use this second type of second transition allowed and halt, going to here or here. Okay. Therefore, M has valid computation histories on W if and only if N has valid computation histories on W. Okay. Of course, if M does not have any valid computation history, that means M does not halt on W. That means M never goes to T or R. N also never goes to T or R, and therefore N can also never go to T prime or R prime. So this is fine. Now the importance of this new machine N, this generic construction. Note that this works. This is called a generic construction, because given any M, I can construct this new machine N. We do not need any special assumption on this M. And the reason for constructing this M is that irrespective of whether this language valcomp M, W is context free or not, valcomp N, W is necessarily not context free. Okay, it's never a context free language irrespective of whether this language is context free or not. Now proving this is not so easy. Of course, we have seen several techniques for proving non-context freeness, pumping lemma, Ogden's lemma, and even some properties of context-free languages. All the techniques that we have seen, I think, will fail to establish that this language is not a context-free language. So I need a more powerful tool. Let me first explain that. So you convince yourself that how pumping lemma or even Ogden's lemma are insufficient to prove that this language is not context-free. So I have to use some little bit stronger result, which is a stronger version of Ogden's lemma. Okay. So this goes like this. Let L be a CFL, then there exists a constant K, such that many things happen. The following thing happens. And that constant K is the pumping lemma constant in connection with this variant of Ogden's lemma. This is not the same constant for, I would say, the original pumping lemma or the original Ogden's lemma. It is constant pertaining to this variant of Ogden's lemma. Now, let us take any string Z in L, which satisfies the following three conditions. First, Z has some D-distinguished positions. Moreover, what is important in this variant is that Z also has some E excluded positions. Okay. And there may be positions in Z which are neither distinguished nor excluded. But if Z has D distinguished positions and E excluded positions, this D and E must satisfy this relation. D must be at least greater than at least K times E plus 1. So in the version of Ogden's lemma that we have seen in the class, we have taken no excluded position. So E was 0. So D has to be greater than or equal to K. At least K distinguished positions. Now, the reason for including excluded positions will be evident from the next slide. Statement says that now only one extra thing. We have a decomposition Z equal to UVWXY as usual, such that first VWX contains at most these many distinguished positions. Okay. More importantly, Vx, that is the parts of Z that we want to pump in or out, they must contain at least one distinguished position, and Vx contains no excluded positions. So this is the new thing that we have now. No excluded positions. No positions which we marked as excluded. And then the final thing, Zi equal to U V power I Wx power I Z is in L for all I greater than or equal to 0. This is the same as in any version of pumping lemma for context-free languages. So now let me use this strong result to prove that irrespective of M and W, the new machine N that we have created satisfies the property whenever it is non-empty, it is never context-free. Of course, if it is empty, then this is definitely context-free, but if it is non-empty, it cannot be context-free. So, how to use that lemma? Yeah. So, take a sufficiently long, okay, since this is non-empty, val comp NW is non-empty, that means there are valid computation histories, in particular finite computation histories. And we can extend such a computation history arbitrarily because the machine now has that transition which may keep on going right and right and right and right in the old acceptor reject state T or R, and these configurations can be made arbitrarily large. Okay, as the machine, the LZ head keeps on moving in T or R to right. So these configurations may become arbitrarily big. And we can add as many as I want, but only finitely many. So I will come to the choice of L, why it is needed. L should be sufficiently large. I will mark all the hashes in this computation history. Okay. So this is another thing. I will not allow any trailing blank in any configuration. Of course, if the head is there, I have to allow that. If the head is not there, I will not allow any trailing blanks. So the symbol blank with on the first track and minus on the second track. We will not allow them in such thing. But if the head is there, I have to include that. So I will mark all the hashes, the separators, as excluded positions, and everything else as distinguished. So in particular, there are no positions here which are neither excluded nor distinguished. We do not need this. Each position is either excluded or distinguished. So in that form also we can use the strong version of Ogden's lemma. Okay. Fine. So now, what is the need for this L? A sufficiently large quantity with big configurations, with long configurations. We somehow should have this condition be satisfied. D greater than or equal to K plus 1. The point is that every time you add a new configuration, you add one hash. So, in order that this thing happens, this CL should grow quite, I would say, depending upon how big this K is, it should be allowed to grow, and we should be allowed to include many such configurations which are growing in length. So if I can choose L sufficiently large such that this condition is satisfied. Now I can apply the strong version of Ogden's lemma. So which says that the pumpable portion of that Z, this is Z, will not contain any hash. Okay. Which immediately implies that if V is non-empty, it cannot span across multiple configurations. Likewise, if X is non-empty, it cannot span across multiple configurations. So V or X, whichever is non-empty, possibly both, must reside inside a single configuration. What is the implication? Now you can just pump in or pump out Vx once, and it is easy to see that by doing so, you are introducing some inconsistency among consecutive configurations. At least one inconsistency is introduced. Okay. So, Z is neither Z0 nor Z2 is in L. That is a contradiction. So, for that reduction, HP complement to the set of all languages, context-free languages, whose complements are again context-free. You first construct N from W and N from M and generate the grammar for the complement of this language, not M, W, N, W. Okay. Now the proof is correct and complete. Okay. There is another thing which we have used in the exercises, in the exercise solutions to be more precise, is that although the complement of val comp M, W is a context-free language, it is not a DCFL. Now this result holds irrespective of any M and W. We do not need any generic construction now. Whatever M and whatever W are, this language, the complement of this, is never a deterministic context-free language. Why? The reason is that take any string which is not a valid computation history, maybe it is of this form. Now there will be multiple reasons all acting together which make this a non-valid or invalid computation history. So there will be syntactic reasons like C0 is not the start configuration, some configuration contains multiple or no states, Cn is not a halting configuration, and there will be semantic reasons too, like multiple inconsistencies among consecutive pairs of configurations. So all these things may be simultaneously present in alpha, and therefore you cannot discard alpha to be a valid computation history for a unique reason. So that means what? Alpha has multiple parse trees for belonging to this context-free language. Right? That means whatever grammar we write for this has to be ambiguous. In other words, this language is inherently ambiguous. Okay. Now, so when I say that, I have made use of one important result which we have not proved in the class because it's slightly beyond the scope of this course or our coverage. That is, a deterministic context-free language is inherently unambiguous. Therefore, if this is inherently ambiguous, we cannot write a deterministic context-free grammar for this language. And that happens irrespective of M and W. We do not need any specific construction, like converting M to N. This is true for any M and any W. So this is never a deterministic context-free language, although it's a context-free language. Okay, so these are all for now. So these clarifications essentially originated from a discussion between the two teachers. If you require some more clarifications on this or other topics, please let us know. If necessary, if possible, we will send emails or clarifying, I would say, notes. If necessary, we will try to prepare more videos on clarifying details. I hope you are doing well, so take care. And please note that possibly we will not have an opportunity to go through a few doubt clear sessions. Anyway, so please communicate with us if you have any problems regarding these topics. So take care. Bye.